Hello, everybody. So today we're starting a sequence of videos on advanced topics. And this video is going to be about proofs, advanced topics on proofs, and we'll see how the computational lens changes the meaning of proofs, changes the notion of what we can prove and in what ways can we prove. And this topic of all the topics that we're going to see is the most closely related to what we've seen in this class, and it contains some of the most beautiful results in theory ever. So I highly recommend watching it. Of course, in all of these advanced topics, the level of understanding that I'll expect will be much weaker than in the main thread of the course. I mainly want you to be aware of these beautiful results. So, coping with NP-completeness. There are thousands of NP-complete problems, and they are very interesting, and they are in many areas, and we can't ignore them. So many of them are solved all the time, although they are NP-complete. And there are various ways in which we handle NP-complete problems. That's referred to as coping with NP-completeness. The fact that we know that a problem is NP-complete doesn't mean that we are just kind of giving up and continuing with something else. Sometimes we just need to solve it. And there are various ways in which we can solve NP-complete problems. The first one relates to this notion of average case versus worst case complexity. So perhaps we cannot solve an NP-complete problem all the time, but perhaps we can solve it on most inputs or most interesting inputs. It's not easy to define what we mean by interesting inputs, but for particular problems like solving SAT, we have very efficient SAT solvers that seem to be working very well in practice. We don't know how to create problems that these SAT solvers will fail on, but perhaps the problems that we want to give these SAT solvers naturally usually are ones on which SAT solvers work very well. So that's the difference between heuristics and algorithms. With algorithms, we have a proof that they work regardless of the input. Heuristics are ones where they could work on many inputs, but not necessarily on all inputs. We will not talk about that. It's a very large topic of research, and with a little bit of luck, this class here at Stanford can tell you about it. Another thread of coping with NP-completeness is looking at special cases or special parameters that makes a hard problem easy. So we did discuss it a little bit when we talked about subset sum. If the target is small, then this problem is actually easy, is in polynomial time. If we're talking about SAT, 3 SAT is still hard, but if we talk about 2 SAT, so if all clauses are of size 2 or less, then this is easy. And there are many interesting examples of that. And we will not talk about that either. What we will talk a little bit is about approximation algorithms. So let's recall this notion of vertex cover, which was NP-complete. So vertex cover is a set of nodes that cover all the edges. So every edge has at least one of its endpoints in this C. And here we have this as the vertex cover, whereas here we have a vertex cover of size 3. What we want to do is get the smallest vertex cover possible. And the largest is easy. You take all the vertices, it gives you a vertex cover. The question is how to get the minimal vertex cover. And perhaps we will give up on finding the minimal, but perhaps we can find something that's close enough. So approximating vertex cover. This is a minimization problem. We want to find the smallest vertex cover. And a very simple greedy algorithm finds a vertex cover that it is at most twice as large as the optimal. It's a trivial algorithm. And that's what's known as two approximation. And let's see this algorithm. It's so simple. You start with an empty vertex cover, or an empty set that eventually will become the vertex cover. And since it's not a vertex cover, there is some edge that you didn't cover. And what we do is to take both of its endpoints and add it to C. So looks like more intuitive thing to do is to take one of its endpoints, because this is enough to cover this edge. But in fact, we are going to add both of its endpoints. And this will give us two approximation. Taking one could actually be horrible. So if you think about the example from the previous slide with the star, we can, if we take, every time we take an edge, we take the non-center edge, the other side, then we only cover this edge, and we will continue selecting everything but the center. So although there is a vertex cover of size 1, we will find a vertex cover of size n-1. Whereas this algorithm will take an edge, the first edge, it's not covered, it will take both of its endpoints, and one of it is the center, which will then cover everything else. But more generally, why does it work? You can think of that. I'll give you kind of a hint. Whenever we take an edge that's uncovered, one of its endpoints is in the minimal vertex cover. So we are going to add this into C, and in addition, we're adding another one. So every time we add two vertices, one of them is part of the minimal vertex cover, meaning that we're going to add at most twice the size of the minimal vertex cover. Let's give another example, max sat. So with the satisfiability, the problem is maximization. Given a CNF formula, how many clauses can be satisfied? If you can satisfy all the clauses, it means that the formula is satisfiable, and this is the satisfiability question. But the question is, and that's NP complete. So instead, perhaps we want just to maximize the number of clauses we satisfy. And the problem is maximization. It's of course easy to satisfy a single clause, and we want to satisfy as many as possible. So we want a maximization problem. And assume that we are looking at 3-sat. Let's assume that all clauses actually it's even more general than 3-sat. We want every clause to have at least 3 unique literals, but perhaps you have more than that. And now we want to say that I want to claim that you can always satisfy at least 7/8 of the clauses, and pretty efficiently. So of course, the maximal number of clauses you can satisfy is everything. So satisfying 7/8 of the clauses is a 7/8 approximation. Since it's a maximization problem, the approximation number is smaller than 1. How can we do that? As a hint, think about what happens if you select the assignment at random. So for every xi, you select it to be true or false at random. And now look at a clause that has at least 3 literals. Each one of these literals is satisfied with probability half. The probability that none of them is going to be satisfied, and it's independent because they are unique literals. So I'm assuming you don't have xi and not xi, or xi not xi would be a very easy example, but you don't have xi twice. And this means that you won't satisfy a clause with a probability that is at most 1/8. Every clause is satisfied with probability 7/8. This gives a randomized algorithm that satisfies, in expectation, it satisfies 7/8 of the clauses. And this algorithm can be de-randomized, made deterministic, in a way that it satisfies at least 7/8 of the clauses. But okay, we've done that. The question is, can we do better? Can we approximate it, for example, to 90%? Can we even solve it with 7/8 plus some small constant, epsilon? Can we have a 7/8 plus epsilon approximation? That turns out to be no, or at least not unless P is equals to NP. If P is equals to NP, then you can solve satisfiability exactly, and you can solve maxstat exactly. So you can have a one approximation, which is not an approximation, it's an optimal algorithm. For every value you can verify in polynomial time, can you satisfy for every t, can you satisfy t clauses? And you can, for example, with the binary search, find the best t. So you'll find the maximal number of clauses you can satisfy. So if p equals NP, this is easy. If p is different than NP, it's not only that you cannot solve it exactly, and we know that you cannot solve it exactly because if p is different than NP, you cannot solve SAT. And if you cannot solve SAT, you cannot solve maxsat exactly. But you can't even approximate much better than 7/8. And that's pretty amazing. For other problems, we can even prove things that are much more strong. For example, for clicks, not only you cannot have any constant approximation of the click size. So given a click of size k, that there is a click of size k, you cannot find a click of size k over 10. But in fact, you cannot find a click of size k over n to the 1 minus epsilon. So even if there is a click that's pretty huge, it's larger than n to the 1 minus epsilon, you cannot find a click that's pretty tiny. It's smaller than n to the epsilon. And the question is, how do we derive all of these results? And how can we use NP-completeness that is not about approximation to show things that are, to show results, such strong results about approximations? This brings us to the PCP theorem, probabilistically checkable proof theorem. And perhaps in the way I'm going to define it now, it wouldn't be clear why is it called PCP, but we will see another way of stating it that would make the term PCP much clearer. So here is the PCP theorem in this presentation. For some constant alpha larger than 0, and for every language L in NP, there exists a polynomial time computable function. So this is a polynomial time reduction, f, that maps every x into a 3CNF formula fx. So far, it's just like the Cook-Levin theorem. Let's see what happens, such that if x is in L, then f of x is in SAT. Again, still like the Cook-Levin theorem. But if x is not in L, there is no assignment that satisfies more than 1 minus alpha fraction of the clauses of f of x. So this is where we depart from the Cook-Levin theorem. It's a stronger version of the Cook-Levin theorem. In the Cook-Levin theorem, we would say that if x is in L, then f of x is satisfiable, and if x is not in L, then f of x is not satisfiable. That's the standard reduction. Here we'll say that there is no assignment that satisfies more than 1 minus alpha fraction of the clauses. What can we conclude from it? We can conclude that a sufficiently good approximation of max_sat implies P equals NP. So if you can approximate max_sat well enough, then given a satisfiable assignment, a satisfiable formula, perhaps you won't find a satisfying assignment, but you will find an assignment that satisfies 1 minus alpha over 2. And this will mean that you are in the first situation, because if X was not in L, then no assignment would satisfy so many clauses. So being able to approximate max_sat well enough means that you can separate these two cases, meaning that you can decide if X is in L or X is not in L. This is not exactly what I promised. I promised that we can show that there is no 7/8 plus epsilon approximation. And for that, we need to work harder and to have a stronger notion of PCP theorem. And that's beyond the scope of this course. So hardness of approximation. This is a very, very rich literature. Lots of beautiful results that show that for particular problems, we cannot approximate them as much as we want. So not only we cannot solve them exactly, this is the NP-Completeness literature. Here with the hardness of approximation, we can show that you cannot approximate them to the extent you want. And interestingly, for many problems like the max_sat, we know exactly what is the best approximation factor. And that's true for a large variety of problems. In fact, we can characterize many families of problems for which we know the exact approximation value. We have algorithms, often very simple algorithms, that approximate these problems within some parameter, and we know that we cannot do much better unless P equals NP. Very strong literature. How do we get these strong inapproximability results? We get them first via stronger PCPs that are fine-tuned to the result that we want. And we also get them through reductions, like we like to do. But now we need to separate reductions to those that are approximation preserving and those that are not. And I'll give you 2 examples that we're already familiar with that will show you these two different notions. So the reduction from 3SAT to click is very approximation preserving, because the size of the click corresponds to exactly to the size to the number of clauses you're going to satisfy. And therefore, if you can approximate one, you can approximate the other within exactly the same parameter. On the other hand, independent set is reduced to vertex cover, but this is really would not preserve approximation factor. So approximation of the vertex cover would not imply a good approximation of the independent set. And we'll see that in a second. So let's start with that. This is the click. We showed that if the formula is satisfiable, then there is a click of maximal size. But in fact, if you can satisfy some R number of clauses, it will correspond to having a click of size exactly R. And therefore, if you can approximate click, you'll be able to approximate max_sat. And so this means that you can get inapproximability of max click via the inapproximability of max_sat. So the max click equals the max_sat. And approximating the max clique implies approximating the max set. On the other hand, if you look at the independent set to vertex cover, what we've seen, the claim was that for every graph, a subset S is an independent set if and only if V minus S is a vertex cover. So GK is independent set if and only if G, let's call it N, the number of vertices. So Gn minus K is a vertex cover. And now you can see that approximate this number within some factor doesn't imply approximating this value because there are very different values. So let's look at that. Assume, for example, that the minimal vertex cover is very small. It is K. Perhaps there is a vertex cover of size K, and K is much smaller than N. This means that the maximal independent set is N minus K, so pretty close to N. If you have a C approximation of the independent set, what it means is that you'll get independent sets of size N minus K over C, which is N over some other C prime. It's because N minus K is very close to N. This is an approximation within a constant. So what does it give? It gives us a vertex cover of size N minus N over C. But we know that the vertex cover is very, very small. It is almost, it is much smaller than N, and we give you an approximation that is very large. It's close to N. Let's say it's larger than N over 2. So this is not an approximation at all, or not a valuable approximation at all. This particular reduction is not approximation preserving. And we can develop an entire theory of reductions again and see what are approximation preserving reductions, and that would help us develop. And indeed, this literature about hardness of approximation does that. So let's kind of abandon this motivation of hardness of approximation and look again at this notion of PCPs, which, as I said, is called probabilistically checkable proofs. And to understand why it is called this way, we need to look at a different formulation of this statement. So an alternative equivalent statement of the PCP theorem is, in an informal fashion, is the following. Every statement that has a polynomial time verifier, polynomial time verifiable proof, has such a proof, so still it's polynomial time verifiable, but it can be verified by a verifier that only reads a constant number of bits in the proof. So imagine that. It's I give you a proof of an amazing theorem, for example, of the PCP theorem, and to be convinced that the proof is correct, you don't need to read it. I don't know, to read all 100 pages of it. Instead, I can give you a different formulation of the proof, and you will only read a few bits, and you'll be convinced if the proof is correct or not. Let's give a few more details because, to be more exact. So there is a verifier that reads only a constant number of bits of a proof, such that if the statement is correct, you're going to accept the proof with probability 1. So if you really gave me a proof of the PCP theorem or whatever other theorems of P equals NP or different than NP, I will never tell you, oh, I think you're lying. Perfect completeness. If the proof is correct, I will never say it's not correct. And you have some soundness. If the statement is false, you're going to reject it with probability 99%. And if 99% is not good enough, you can repeat it enough times, and this will make it as small as you want. Instead of reading some constant number of bits, you can read a larger constant and get to really tiny probabilities, which we could accept. So So why are we calling it PCPs? These are proofs that we don't verify deterministically. We don't go over them one statement at a time, but instead we verify them probabilistically. We sample them in a few places randomly, and we have some good probability of being correct. Pretty amazing statement if you think about it, and I do recommend that you think about it. So this is an example of the power of randomness, and we're actually going to talk more about randomness in one of the future videos. So what can we prove? Every problem in NP has a short proof that is easy to verify. That's the definition of NP. These are problems that can be verified efficiently. But what about other problems? We said that there are interesting problems beyond NP, such as in co-NP. Can we have a prover that convinces a verifier that there is no k-click? I can definitely convince you that there is a k-click by showing you the click, but can I convince you that there is no k-click? How about p-space? Can I convince you? So we talked about some of these games being complete for p-space. Can I convince you? Is there a p that can convince a v that there is a winning strategy from a particular chess position? Sounds amazing. I mean, NP is the definition of what you can prove. Now I want you to prove things in co-NP or even p-space. Sounds kind of impossible, but turns out to be possible if we add to the standard, to the classic proofs, the randomness that we already added for getting PCPs, and also interaction. So if we think of proofs not as something that's written and we read it, but kind of an interrogation, like an interrogation in court, then we can get a way to prove statements that are much, much stronger. Every statement in p-space. So this kind of brings us to this notion of interactive proofs. So PCPs add randomness, and we are going to add interaction. We have a prover, we have a verifier, and we have something that we want to prove, some statement, for example, that X is in some language. And the verifier asks questions of the prover gives answers, so they interact, like Alice and Bob in the communication complexity, but now the verifier at least is going to be, would not need to be particularly powerful. At the end of this interaction, the verifier accepts or rejects. And we have that interactive proofs can be used to prove membership in powerful languages in p-space. So for example, you can prove that you know a winning chess strategy. This is the famous IP equals p-space proved by Shamir. The notion of accept and reject is exactly like we had before. We have completeness and soundness. If X is in the language, then you will accept with probability 1. If otherwise, you'll reject with probability 99%, which can be amplified. So let me give you an example of an interactive proof. This is a little bit like wine tasting. Let's say that I tell you that, you know, I can really tell an expensive wine from a cheap wine. I'm very good at that. Or even that I can separate Pepsi from cola. Then you can give me a blind tasting. You'll give me 2 glasses of wine, and you tell me, okay, tell me which one is the cheap and which one is the expensive, or which one is Pepsi, which one is cola, or you can just give me one of them at random and I need to tell you. And if we'll repeat this experiment many times and I'll consistently say the right thing, you'll be convinced that indeed I can separate the two. I personally did the wine tasting once and was convinced that good wine is a waste on me. I really preferred the very cheap wine. I thought it's very expensive, and the very expensive I thought is not very special. So let's see what is this graph non-isomorphism or isomorphism. Graph G and H are isomorphic if you can rename the vertices of G to get H. So they're the same up to renaming. We talked about isomorphism way before in this class. The mapping of name is called isomorphism. So I can change the names, and then the graphs will turn out to be the same. Graph isomorphism is GH such that G and H are isomorphic, and graph non-isomorphism is GH such that G and H are not isomorphic. Recently, there was a lot of progress on that problem. We still don't know that it is in P. And definitely the way we can prove, the algorithms for graph isomorphism that we know today that are still not polynomial exactly are also very complicated. And instead, I'm going to give you a very simple proof, interactive proofs of graph non-isomorphism. So graph isomorphism is in NP, but can we prove that G and H are not isomorphic, right? It's not easy to imagine how you'll do that. And definitely, unless you prove that that graph non-isomorphism is also in NP, there isn't a proof that you can write down that the graphs are not isomorphic. Because to show that two graphs are isomorphic, it's enough to show the isomorphism. To show that they are not isomorphic, you need to claim that there is no isomorphism, which is seems much harder. We will show a very simple interactive proof. So here is an interactive proof for graph non-isomorphism. You have two graphs, G0 and G1. You have a prover and a verifier. And the prover wants to claim that G0 and G1 are non-isomorphic. So what would the verifier do? The verifier would select a bit at random. So it's like selecting whether to give you for tasting Coke or to give you Pepsi. If it's B, you're going to take G0. If B equals 0, you're going to select G0. If B equals 1, you're going to select G1. And then you want to give it to the prover P, and the prover should tell you what is B, which one you selected. But doing just that is like selecting Coke and then give you a can of Coke, and you see that it's Coke, and you immediately know what it is. So it's not about the tasting, you just see it. So I need to disguise it. So instead of giving you just GB, I'm going to give you H, which is a random isomorphic copy of GB. So I take GB and I rename its vertices at random, and I'm going to send H to the prover. Now, if G0 and G1 are non-isomorphic, then H is isomorphic to exactly one of them. H is isomorphic to GB, and it's not isomorphic to the other graph, because otherwise we will get, by composing, an isomorphism between the two. So find C such that H and GC are isomorphic, send C, and the verifier accepts if C equals B. So if the verifier chose Coke and disguised it, and the prover said, yeah, it's Coke, then you'll accept. If the verifier chose Pepsi and disguised it, and the prover said that it's indeed Pepsi, then the verifier will accept. But if the prover chose the wrong bit, then it's going to reject. This is the proof. And it's a proof of a very powerful statement, and it's a trivial proof. So even if tomorrow somebody will prove that graph non-isomorphism is in NP, but you'll do it in a very complicated way. This proof is very simple. What will we have? We have perfect completeness. If G0 and G1 are not isomorphic, then V would accept with probability 1, because P could with probability 1 identify B. And we have soundness half. If G and 0 and G1, if G0 and G1 are isomorphic, then H is an isomorphic copy of both of them, and the prover cannot tell which it is, apart from guessing. So it can only succeed with probability half, no matter what it does. And we can, again, by repeating this experiment, we can improve the soundness. So we can make it probability 1 versus probability 1%. I want to show you one last idea, last brilliant idea. And this is this notion of zero knowledge interactive proofs. So we saw that interactive proofs already give you this amazing power. You can prove things that are much more complicated than NP. And in fact, you can do something else. You can give zero knowledge proofs. So the prover is going to convince you that X is in L. But zero knowledge proof will reveal no information apart the fact that X is in L. So think back to, or think even about satisfiability. So even problems in NP, it's not obvious how to do that. So if I'm the prover and I know a satisfying assignment to a formula, I can convince you that the formula is satisfiable by giving you the satisfying assignment, but I'm doing much more than convincing you that the formula is satisfiable. I'm telling you what is the satisfying assignment. Can I prove it to you without revealing any information about the satisfying assignment? Turns out that you can, and you can do it not only for NP, you can have zero knowledge proofs for all of the interactive proofs, meaning for all of P space. Every problem in P space has an interactive proof, and in fact, it has a zero knowledge interactive proof. So you get soundness, and you have completeness, and you have zero knowledge. Let me give you a quick example, and which is, again, exactly the same protocol that we saw before, the zero knowledge, the interactive proof for non-isomorphism. And I want to claim that it is a little bit zero knowledge. It's zero knowledge for what's known as semi-honest verifier. So if the verifier follows the protocol, but tries to learn a bit more after the fact, so for example, even in the proof, the NP proofs that we wanted to say, I'm going to send you a satisfying assignment, the verifier doesn't do anything wrong. It gets the satisfying assignment, but now it knows much more. So here the verifier is going to follow the protocol, but at the end tries to learn more, and we'll see that it cannot. And in fact, there is a not much more complicated zero knowledge proof that doesn't make any assumption about the verifiers. But let's see what happens. H, so we had G0 and G1. They are non-isomorphic. And I'm sending you H, and I'm getting C. Now, if I know that it is non-isomorphic, and if I assume that the prover is following the protocol, then the verifier can simulate the protocol by themselves. They're going to select H, and now they can imagine that the prover has sent them B. So what the prover is going to send is completely predictable. I don't need to, if I believe the prover, if I believe that the graphs are non-isomorphic, I don't need the prover to simulate the interaction. I can create an interaction on my own that is exactly like the interaction that I would have interacting with the prover. So the prover taught me nothing, apart from the fact that the two graphs are non-isomorphic. It is extremely high level. There's much more to tell, many more beautiful examples. Be happy to show you a little bit more when we meet. I'll also give you a link to a paper that tries to illustrate this notion through this game or this puzzle known as Where is Waldo? You have this picture with lots of characters, and there is one special character that's called Waldo, and you want to find it. And the question is, let's say both of us are playing, and I say, you know, I already found it, and you don't believe me. How can I prove to you that I know where Waldo is? I can point Waldo to you, but then the game is ruined for you. You would not enjoy it anymore. You can find it. So how can I prove to you without telling you anything else, without helping you find Waldo? So there are a couple of nice ideas there, and I hope you'll enjoy it. So kind of parting thought is that the computational perspective of proofs really gives a lot of beautiful results. When traditionally this notion of a proof was very clear, you had these things that you assume, you have ways to deduce, and you reach a conclusion. And it's something that can be verified one statement at a time with probabilistic approach and with interaction. And later, if kind of assuming some bounds on the power of the verifier, you get beautiful results, such as this notion of zero knowledge, and 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 the beautiful theorem that IP equals P space. Thank you.